A single keystroke generates an electrical impulse that travels from your hardware to a remote server, initiating a massive computational event. For an autocomplete system, the objective is to predict user intent and deliver highly relevant search suggestions in the gap between this keystroke and the next. That gap imposes a strict physical constraint on the entire system design. The architecture has exactly 100 milliseconds to return an answer. Any slower, and the user's next keystroke overrides the interface. A common starting point is to rely on standard data retrieval. You take the user's prefix, send it to a relational database, and execute a wildcard query to find every row that matches the string. Look at this database table. When a query for the prefix CAR hits it, the database engine must scan for all possible matches, aggregate them, and sort them by popularity. The time this takes scales linearly with the size of the corpus. With millions of records, the 100 millisecond budget expires long before the scan finishes. Multiply that latency by the tens of thousands of read requests coming in every second at Google or Amazon scale, and a standard database immediately locks up under the load. Building a system at this scale is a struggle against the physical limits of time and request volume. The standard computer science solution to prefix matching is a specialized data structure called a Trie, or prefix tree. A Trie stores data character by character, forming complete queries. To find completions for car, the search algorithm takes just 3 steps to the R node, completely bypassing the rest of the dataset. Finding matches is only half the requirement. A standard Trie has no inherent concept of popularity. To find the most relevant suggestions, the algorithm must scan every single node in the subtree below the prefix, aggregate their scores, and sort the final list. Mathematically, this is an O of C log C operation, where C is the number of children in that subtree. If a user types a single letter, like S, that subtree contains millions of nodes. While the Trie isolates a prefix efficiently, relying on it to rank suggestions at read time guarantees a latency failure. To survive the 100 millisecond budget, the architecture requires a structural shift. We have to remove the sorting operation from the user's request path entirely. This is achieved through the ranking inversion principle. Instead of computing top suggestions while the user waits, the system stores the final ranked answers before the user even begins typing. We augment the Trie by embedding a pre-sorted list of top completions inside every node. When a keystroke reaches the R node, the algorithm stops. It executes an O of 1 retrieval, grabs the cache table, and returns it. There is no subtree scan and no sorting. Storing duplicate lists of top suggestions at every single node requires significantly more RAM than a standard tree structure. By trading memory consumption for latency reduction, the system guarantees a sub-100 millisecond response, regardless of how massive the total dataset becomes. If the serving layer only holds static, pre-computed answers, the system needs a way to detect viral trends and adapt to shifting user behaviors. The solution is decoupling. We must physically separate the ultra-fast read path that serves the user from the heavy write path that processes the data. On the write path, raw search and click events stream into aggregator workers that batch them into uniform metrics. Those metrics are written into a scalable NoSQL database like Cassandra, stored in time-bucketed columns that group query frequencies by the hour. Without intervention, a historically popular query would permanently outrank a rapidly rising search today. To fix this, the system applies recency-weighted decay. Older time buckets are mathematically penalized, so yesterday's massive traffic spike actively shrinks, allowing fresh, trending queries to rise to the top. Finally, background workers known as applier jobs periodically read this newly decayed data. They rebuild the tries from the bottom up, generate fresh snapshots, and push those updates to the serving layer. Decoupling allows the system to execute computationally heavy data science tasks asynchronously without adding a single millisecond of latency to an active user search. Even with a perfectly optimized structure, an augmented Trie containing billions of global queries will eventually exceed the RAM capacity of a single physical machine. To scale out, the system uses range-based alphabetical sharding, slicing the monolithic Trie vertically to distribute prefix ranges across different servers. Because language distribution is uneven, these splits are dynamic. A dense letter range is subdivided into smaller chunks to keep memory load balanced. Managing this scattered infrastructure requires a dedicated coordination layer, typically handled by Zookeeper. Zookeeper acts as the central map. When a request hits the front end, the system checks this map to determine exactly which physical shard holds the data for the user's specific prefix. By sharding the data, the system ensures that the read path maintains its O1 lookup speed. A request is cleanly routed to a single, highly optimized server, no matter how large the total index grows. This architecture map shows all components in a highly available system. For popular prefixes, requests are intercepted at the edge by a Redis cache, returning instantly. Novel keystrokes bypass the cache, route through Zookeeper to the correct shard, pull the pre-computed list, and return to the user. Because the read path and write path are completely separate, the offline applier jobs can swap out updated Trie snapshots on a replica without dropping a single active read connection. This means the architecture is eventually consistent. It takes minutes or hours for new user behavior to reflect in the UI, an acceptable trade-off to maintain absolute read performance. Typeahead systems rely on a total pre-computation model, where ranked answers to every possible prefix are stored before the user ever touches the keyboard. By anticipating the read, executing all algorithmic ranking offline, and serving answers strictly from memory, this architecture bends massive data scale to fit securely inside a 100 millisecond window.